Hello there, students. Welcome back. This is part 2 of the lecture about the radiation laws that are determining climate. Radiation is going to be one of the ways that we can move heat around in the atmosphere. Moving heat is actually a really complicated topic. Atmospheric science students tend to take classes in a discipline known as thermodynamics. Physics majors do that kind of thing, and so on. Thermodynamics is all about the ways in which heat can move around in a system, from objects that are hotter to objects that are colder. And, a very classic thing to describe is the different ways that you can move heat around in a system. And, pretty much any kind of introductory science textbook is going to talk about the fact that there are lots of ways that heat can move around. In the context of climate, I would say that there's going to be 4 main ways that heat can move around. We're going to be focusing on one of them, but just for point of illustration here, one is conduction. Okay, conduction is when 2 objects are touching and are different temperatures, like the eggs and the pan. The pan is hot, the egg is relatively cool. Heat is moving from the pan to the eggs. In the same way, like when the sun shines on the ground and warms the ground up, heat transfers from the hot ground into the cooler air by conduction. Convection is about moving heat by moving air vertically. Like a warm plume, you might have heard the term a thermal, a warm plume of air rising or cooler plumes of air sinking. That's a way of transferring heat by moving the heated fluid, in this case the heated fluid being air. In the same sort of way, on climate scales, we worry about another way of moving heat called advection. Advection is about moving air horizontally when the different volumes of the air have different temperatures. So this is a diagram that you'll see someday if you take ATS EVS 113, where we're moving air masses, like from Canada, some cold air masses are moving south, some warm air masses from over the Gulf of Mexico are moving north. That transfer of air horizontally when the air has different temperatures is called advection. That's another important way to move heat around on climate scales. But what we're focusing on in this module of the course is going to be radiation. Now, the right term here is actually electromagnetic radiation, and if you needed a definition of radiation, I guess we could say that it is a transfer of energy in the form of waves in the electromagnetic field, which might not seem all that helpful to you. You might be thinking, I'm sorry, but what's an electromagnetic field? That's a really good question that ongoing work in physics is exploring. But we are all surrounded by the electromagnetic field, and there are waves in that field. This is, by the way, when we hear the word radiation, you might get spooked and think, oh, like radioactivity or, something that would make a superhero get his powers or something. That kind of radiation, that's radioactivity, or ionizing radiation is sometimes the right word. That kind of stuff, that's like broken atoms. Those are chunks of broken atoms that are doing things like taking apart your DNA and stuff like that. Like what you need to be worried about when you're talking about radioactive waste or something like that. That's different. This is energy. What is stored in the form of waves in the electromagnetic field. Here I have a picture of some waves on the ocean. And those waves are moving. Think of us as being in the ocean with those waves, okay? That's kind of what the electromagnetic field is like. We are surrounded right now by the electromagnetic field, and there are waves in that field. Now those waves carry energy. It takes energy to make those waves. It gives you energy back when you destroy those waves. Those waves are moving energy around in the same way that the electromagnetic field has waves, and they are moving energy around and so on. One of the key characteristics when we're talking about waves, whether we're talking about waves in water or waves in the electromagnetic field, is their wavelength. The size of the waves from the crest of one wave to the crest of the next wave. One full wavelength of the waves. Now, when we're talking about water, water waves come in a wild range of wavelengths. Like these little ripples might have a wavelength on the order of a centimeter or 2. On the other hand, like this giant ocean swell here that this guy is surfing on, the next big swell of that, train of waves might be, several hundred meters farther out to sea yet. That wavelength could be very, very large. Wavelength is a key parameter to describe the different kinds of waves. Now, there are other parameters as well, but it turns out wavelength is the most important one when we're talking about the electromagnetic waves that make up radiation. There's a whole range of sizes of wavelengths for electromagnetic radiation waves, just like there was for the ocean. Now, actually, the range is far bigger when we're talking about the waves in the electromagnetic spectrum. Um, Here is a classic diagram. You have one very similar to this in your textbook that shows how wavelength, which we use the symbol lambda for wavelength, there is a whole wide range of wavelengths here, going from very short waves on the left to very long waves on the right. You might notice there that there's a scale on that graph that's at the top of the page there, and it goes from 10 to the negative 16th power of meters of wavelength to 10 to the 8th power of meters. Just a quick check here, when we're talking about like 10 to the 8th or 10 to the negative 16th or whatever, 10 to the 8th means 1 followed by 8 zeros. 10 to the negative 16th is moving the decimal 1, but then you move the decimal point 16 places to the left. So it's a very, very small number. You can always think of those exponents as like a 1, and then that's how many digits you move the decimal place to the right. So like 10 to the second power is 100, because you started with a 1, and then you move the decimal place 2 places to the right. Whereas like 10 to the negative 4 would mean you'd be moving the decimal place 4 places to the left. So this is a huge range of wavelengths here, okay? Way over here on the right side of the diagram, these are all what we call long waves. You know, they have wavelengths of meters, tens of meters, hundreds of meters, thousands of meters. Now, admittedly, as we get closer to the left-hand side of that range I have circled there, you know, there's still like, you know, 10 to the negative 4th meters. Okay, that's like, you know, fractions of a millimeter. But as you're going to see, that is actually still a pretty long wavelength to the ones over there on the other side of the diagram, which we call short waves. Short waves have wavelengths that range from like, you know, negative 10 to the negative 7th power down to, you know, 10 to the negative 16th on this diagram here. And these are very, very short, very, very small waves. Their wavelength is very, very small. Notice that what is colored in there with sort of that rainbow is part of the short wave range. Why the wavelengths of this radiation are so important is because the wavelength is what determines what kind of radiation it is. For example, these relatively long wavelength waves are radio waves. They're the kind of waves that are used to communicate from like cell phones to cell phone towers, or radio stations using to communicate, or television is transmitted that way, etc. These are very long waves of radiation. A little bit shorter than that would be microwaves. Microwaves are a type of radiation, though the wavelength is on the order of like centimeters. And they are in fact the type of radiation that like your microwave oven produces to cook your food. That your microwave oven gets its name because the magnetron inside of the oven produces microwave radiation. It is a type of long wave radiation. IR, or infrared radiation, is another type of radiation that is considered long wave radiation, although admittedly it's getting to be pretty small. We're talking on the order of like millimeters now for its wavelength. A lot of what you and I consider like, I want to say heat, but that's not really quite right, like when you have your hand near a light bulb or a heat lamp or something like that, and you can feel your hand getting warmer, that's because there's infrared radiation coming from the light bulb and warming your hand up. Infrared radiation is also a type of long wave radiation. Then we have all these types of shortwave radiation too, like ultraviolet radiation. This is the kind of radiation that causes skin cancer and sunburns and fades fabric and fades dyes and things like that. That is a type of shortwave radiation. It is ultraviolet radiation, or UV radiation. And then there's things like gamma rays and X-rays, which are pretty cool stuff, but they have very short wavelengths, and by and large they don't occur in the Earth's atmosphere. There are some of these forms of radiation that are moving through space from things like supernovas and so on, but they in general don't make it through the Earth's atmosphere. They don't really have a climate impact or anything like that. X-rays are exactly what they sound like. They are the type of radiation that like your dentist uses when she takes X-rays of your teeth or whatever. Notice that there is a little area here that is indicated by that rainbow colors there, and that is visible light. Visible light is a type of shortwave radiation where the wavelength is very, very small. It's on the order of nanometers, and every color of visible light is actually its own wavelength, slightly different wavelength of radiation as well. But visible light is also, light is waves in the electromagnetic field all around us. Just like radio waves are, or microwaves or whatever. It's just the only difference is that the wavelengths associated with visible light are just really, really small. but they happen to be the wavelengths of light that the cells in our eyes are adapted to be able to absorb and to process and produce images and so on. So that's the only way that's different. But all these different types of radiation, in fact, have different ways that they interact with matter. And that's why like a microwave oven does something different than like the radio tower at a where it's transmitting your cell phone signals or whatever, and the machine that creates the X-rays at your dental office and so on. All these different types of radiation are only different in terms of their wavelength, but yet they interact with matter differently. Your book brings up something at this point that I would have avoided if I were the guy writing the book. They mention photons. It turns out that thinking of radiation, be that light or microwave or ultraviolet radiation or radio waves or whatever, thinking of them as waves in the electromagnetic spectrum is just one way to think about them. Turns out you can also describe radiation as particles called photons, where you don't think about like the lights around me are transmitting radiation to me in the form of these very small wavelengths of shortwave radiation. We call that light. Another way to think of it is that little particles of light called photons are streaming from the light fixtures and encountering me. Okay, that's another way to think about light. In fact, it's kind of interesting, and frankly any kind of electromagnetic radiation. We'll use the words waves and photons interchangeably, but it's actually a little bit uncomfortable. I mean, this is the book should never have gotten into this. The book says photons have a characteristic size, referred to as its wavelength, which determines how the photons interact with the world. Well, I would agree. The wavelength is what determines how this radiation interacts with the world. Like, does it transmit through the glass because it's the glass is clear, or does it get absorbed by the cells in your body or whatever, or by the water in your food if we're talking about microwave radiation. I don't want you to have the idea though that like photons have a size. Okay, they're a quantum particle. They don't really have a meaningful size. Think of it as more like a tag. They are tagged with a number that is their wavelength. Okay, it's just a property they carry. So if you actually need to think about wavelength, like crest to crest, that's good, then wavelength means something. If you're talking about radiation in terms of photons, the idea of wavelength doesn't actually have a physical meaning. It's more just like a tag that those particles are carrying. It is okay to say that photons have a wavelength, and that wavelength determines the type of radiation it is. I'll buy into that, but the book should never have gotten into this. This is a much too complicated thing to be thinking about when we're talking about climate processes and so on. Before we then start actually taking this idea of radiation and then saying what are the rules that determine how much radiation is moving through the Earth's atmosphere and how that changes the temperature and so on, and how the temperature changes the radiation, let's do, I don't know, about 2 more questions or so. Here's question 4. The wavelength of infrared radiation is blank that of visible light. A, shorter, longer. A, shorter, B, longer, C. It's a trick question, they're the same wavelength. Okay, click on one of the 3 options below this video to get some feedback before you move on to question 5.